In my previous lecture series, you all learnt about the topics related to semiconductors, conductors and superconductors. In this lecture series, I am going to give you an insight on the dielectric materials. We are going to discuss the properties of dielectric materials, the types of dielectric materials, and few theories related to it. And we are also going to understand how dielectrics are useful in practical application, especially in the capacitors. How these dielectric materials enhance the capacitance of the capacitor and how such capacitors are useful in our engineering applications. Such things will be covered in this series of lectures. Understood the differences between semiconductors, conductors and of course the superconductors. In this module we are going to understand the properties of dielectric materials, which are very useful in many engineering applications, especially in the capacitor. This dielectric is very essential. The dielectric materials are essential for capacitors for enhancing their capacitance. What is capacitance? It is the ability of a capacitor of storing charges. So in order to store the charges, a capacitor is required, but for enhancing its ability to store the charges, the dielectric material is required. Now let us understand what are the dielectric materials. The dielectric materials are basically insulating materials. They have the ability of undergoing electric polarization, but in the presence of external electric field. And in some special cases, even in absence of external electric field, some dielectric materials will be electrically polarized. We will come to that point later. So basically, dielectric materials means they are the insulating materials undergoing electrical polarization under the effect of an electric field. There are many examples for dielectric materials. For example, air that we breathe is also an insulator, so that can act as a dielectric material in a capacitor. Mica, paper, distilled water, wood, they are all the insulating materials but having the dielectric properties. And what is electrical polarization? Because that is the basic mechanism that we need to understand in order to address the dielectric materials properties. It is very simple. It is just displacement of electrical charges within an atom or within the molecule of a given substance. Now this can be understood in a better way if I take the example of a capacitor. We all know that the capacitor has the metal plates which are in parallel arrangement separated by a distance, and that capacitor is provided with a dielectric material also. Dielectric material means, as we have already understood, it is an insulating metal in which the free electrons do not exist, means the electrons do not move from one region to the other region within the dielectric materials. They are localized. The electrons, nuclei, ions, dipoles, they are all said to be the charged particles in a given material. Now let us understand the polarization mechanism. Let us assume that these are the plates of the capacitor. They are separated by a small distance. And if they are connected to a battery or a cell, what happens? The plates will be charged. The one which is connected to the positive terminal of the battery will be positively charged. The other one will be negatively charged. And now it has a capacitance. As I already mentioned, it is the property of a capacitor of storing charges. And now in presence of these charges on the plates, one electric field is established from positive plate towards the negative plate. And if you insert a dielectric material between the two plates, what happens? The electrical polarization will take place due to the effect of the electric field that has been established between the two plates. We know that the dielectric material is comprising of the atoms or the ions or the molecules. And we know that a dielectric material in absence of an electric field will have the neutral atoms. Means the charge of each atom is 0 in general. When we apply an electric field, there will be a slight displacement of electrons and the nuclei within the atoms themselves. This kind of displacement of the nuclei which are positively charged and the electrons which are the negatively charged particles is known as the electrical polarization. Now each atom is said to be a dipole because now it is having two poles, electrical poles, positively charged pole and the negatively charged pole. Therefore, every atom is known as the electrical dipole. If it is the molecule, then the molecule is known as the dipole. So, in presence of the external electric field that has been applied between the two plates, the electrical polarization has happened. Now, the charges at the interior portion will cancel their effects, but at the surface of the dielectric material, the charges will remain unaffected because there are no opposite charges nearby in order to cancel their effects. Therefore, negative charges will be accumulated closer to positively charged capacitor plate and positive charges are accumulated closer to the negatively charged plate. As a result, the dielectric material now is acting as a polarized material, having negative pole on positively charged plate side and positively charged end on the negatively charged capacitor plate. The definition of electric dipole. I have already mentioned in the previous slide that the dipole may be an atom or a molecule in which the electrical charges are separated by a small distance. Now let us have a look at the electric dipole. This diagram shows you a molecule or an atom in which the center of the positively charged particles are the center of the positive charges, center of the distribution of positive charges and the center of the negative charge distribution are separated by a small distance d. Now this dipole is said to have a dipole moment mu, which is defined as the product of the magnitude of any one of the two charges and the distance between the two charges in the dipole. And the unit used to measure this dipole moment is the Coulomb meter. Classification. Now let us understand how the dielectric materials are classified. Based on the availability of the dipoles in a given dielectric material, the dielectric materials are classified into two classes. One is the non-polar dielectric, the other one is the polar dielectric. In the non-polar dielectric materials, permanent dipoles do not exist. They are the materials in general comprise usually the diatomic molecules. That means they are composed of two atoms of the same type. In absence of an external electric field, the centers of gravity of positively charged particles that are the centers of the nuclei and negative charge distribution centers are coincided. When an external field is applied, these centers are displaced apart by approximately about an angstrom, that is 10 power minus 10 meter. Now these molecules are said to be polarized and become dipoles, which are known as induced dipoles. These induced dipoles will disappear on removing the electric field. For example, in methane, benzene, etc., this kind of phenomenon can happen. So, non-polar dielectrics are the dielectric materials having no permanent dipoles. That means in them, the positive and negative charge distribution centers are not separated. They are coincided in absence of an electric field, but they are separated when an external electric field is applied. And the second classification, I was saying that it is the polar dielectric. And in these polar dielectric materials, permanent dipoles exist, even in absence of the external electric field. But these dipoles are randomly oriented in absence of the electric field. And while discussing about the types of polarization mechanisms, I will tell you how the polar dielectric materials will be polarized. So polar dielectric materials have the permanent dipoles. Usually the materials having the molecules having two or more atoms of different types will show this property. Their molecules are composed of two or more atoms of different types, and in absence of external electric field, as I mentioned, the centers of gravity of positive and negative charge distributions are not coincided, but normally they are randomly oriented, that is in absence of the external electric field. That is because of the thermal agitation. However, when the field is applied, they all orient in the direction of the electric field. There are few examples of polar dielectrics like water, ammonia, HCl, etc. So these are the materials showing this kind of property. So dielectric properties being poor conductors of electricity, perhaps because of this particular insulation property, the dielectrics are most interesting and useful for electrical engineering materials. And these materials, as I mentioned, are useful in the capacitors. How it is useful for capacitors? That is what we need to understand. For that we need the definition of a parameter that is known as the dielectric constant. Dielectric constant can be defined as a factor by which the capacitance of the capacitor can be increased. We have a relation for the dielectric constant. The ratio of the capacitance with dielectric material between the plates of the capacitor to the capacitance without the dielectric material, that is with vacuum. So C material divided by C vacuum gives you the constant, that is the dielectric constant. It is also called relative permittivity. There is one more relation for the dielectric constant, in which the electric flux density capital D is directly proportional to E, capital E, that's the electric field. Here epsilon naught represents the permittivity of free space. Its value is a constant which is 8.85 into 10 power minus 12 farad per meter. And epsilon r is a unitless quantity. And electrical polarization is another parameter to be understood. Okay, before going to that, let me clear how the capacitance is increased. Here we are observing in this equation that the epsilon r is depending on the ratio of these capacitances, capacitance with material. That means a material that doesn't have the dielectric material will have epsilon r equal to 1, because epsilon r is equal to 1 for vacuum and nearly equal to 1 for air. But it is having a higher value for other dielectric materials. For example, for water, mica, paper, etc., epsilon r is higher than 1. Epsilon naught is a constant. It is not affected by any other physical parameters because it is a constant. So that C vacuum has the value epsilon r equal to 1, whereas C with material will have greater than 1. Therefore, if any material having epsilon r higher, about let us say 80, 100 or 200, 300, the capacitance of the capacitor will be higher. For example, if C vacuum is 1 microfarad, for the same capacitor having that 1 microfarad of capacitance, it is possible to have the capacitance equal to 100 microfarad by inserting a dielectric material of dielectric constant equal to 100, so that the capacitance will be enhanced by 100 times the capacitance of the capacitor without the dielectric material. Now let me tell you about the electric polarization. It's a physical quantity defined as the average dipole moment per unit volume. Because when an electric field is applied, the dipoles are formed or induced, hence they will have a moment, dipole moment mu, and the net value of mu per unit volume of the material, dielectric material, is known as the electric polarization. And dipole moment is defined as the product of the charge, that is the magnitude of one of the two charges in the dipole, and the distance between them, T. Qt gives you the dipole moment, and volume can be measured in terms of the area of cross section and the thickness T of the material, so that you can get the ratio Q by A. That means electric polarization can also be defined as the charge per unit area. Here don't have the confusion between the polarization which I defined earlier and this polarization. The polarization, electrical polarization term used earlier referred to a phenomenon of displacement of electrical charges. Here this parameter, electrical polarization, refers to a mathematical ratio, that is charge per unit area of the dielectric material or the dipole moment per unit volume. There is one more relation for the electrical polarization with the electric field E. Electrical polarization is equal to epsilon naught into epsilon r minus 1 into E, but epsilon r minus 1, because after rearranging this equation you will get P by epsilon naught E. There is a theory which shows that epsilon r minus 1 is equal to the susceptibility. This is known as dielectric susceptibility. So in terms of this susceptibility, it is possible to express the dielectric constant as well as the electric polarization. Now we are coming across the types of polarization mechanisms. There are importantly 4 types. The first one is electronic polarization. In this case, if you consider that this is an atom having the nucleus at the center and electrons around it. Although the electrons are not shown in the different orbits, just to understand the basic things that the electrons are around the nucleus, they are shown as the dots, the red dots. This electron, the center of the charges of these negative electrons and the center of the nucleus are coincided in absence of the electric field. Whereas when an electric field is applied, that is when E is greater than 0. If it is the positive side or positive end of the electric field, then the negatively charged electrons obviously shift towards this positive side and the nucleus towards the negative side. So within the atom itself there is a slight displacement of the nucleus and the electrons. This is what I explained earlier about the electrical polarization mechanism. So the displacement of charges within the atom. So now this atom is the electric dipole. This is not the dipole because here centers of the positive charges and the center of gravity of the negative charges are coincided. So that this is not the dipole, the second one is dipole. So this kind of displacement of electrons and the nuclei within the atom in presence of an electric field is known as the electronic polarization. There is one more physical parameter known as electronic polarizability, alpha E. It is defined as the dipole moment per unit electric field, mu by E in general. Here mu subscript E represents the electronic dipole moment and this is the electronic polarizability. We have defined the polarization as the dipole moment per unit volume. In the previous slide, I had defined that polarization is the dipole moment per unit volume. It can also be shown in terms of this equation. N alpha E. If N is the number of dipoles and alpha E is the electronic polarizability, capital E represents the electric field, then polarization is also given by this equation. Since alpha E into E is mu E, we can express even in these terms. And using this equation, it is also possible to obtain one more relation, that is epsilon r minus 1 is equal to n alpha E by epsilon naught. As I mentioned earlier, epsilon r minus 1 is the chi, that means it is the susceptibility. The second one is the ionic polarization. This happens in the case of the ionic materials, ionic dielectric materials. In this case, displacement of the negative and positive ions will take place. Assume that this is a dielectric material in which the negative and positive ions are distributed in a way that their distances can be assumed to be equal, that is in the absence of electric field. When an electric field is applied, that is when E is greater than 0. If you think this is the positive side and that is the negative side, this arrow mark indicates that the tile indicates the positive end of the electric field and the arrowhead indicates the negative end. So in presence of the positive and negative sides of the electric field, these ions are displaced within the dielectric material. Negative ions will be displaced towards the positive side of the electric field and positive ions will be shifted towards the negative side of the electric field. So such displacement of ions within the dielectric material in presence of an electric field is known as the ionic polarization. And as I mentioned, the relation for the ionic polarizability, earlier we had taken electronic polarizability. Here alpha I represents the ionic polarizability, which is the ionic dipole moment per unit electric field. The other one is the orientation polarization or dipolar polarization. This kind of polarization takes place especially in the permanent dipolar material, I mean the polar dielectrics. Assume that the material is having the randomly oriented dipoles in absence of the electric field. As I was talking about the polar dielectrics earlier, the dipoles are randomly oriented because of the thermal agitation in absence of electric field. Here the arrow marks are representing the dipoles. For representing the electric field, the tile represents the positive end, but for a dipole, the tile represents the negative end of the dipole. The arrowhead represents the positive end of the dipole. Remember this. Electric field is represented in such a way that the arrowhead indicates the negative side of the electric field. Here in the case of dipoles, arrowhead represents the positive side. So in absence of this electric field, the dipoles are randomly arranged, but when the electric field is applied, they rotate themselves in such a way that their positive ends will be oriented towards the negative end of the electric field and vice versa. So this kind of orientation of the dipoles in the direction of the electric field is known as the dipolar polarization. In order to calculate the orientation polarizability, a similar equation which we took earlier can be used. Here mu naught represents the dipole moment of the orientation or dipole moment of this polar dielectrics. And many different properties. In order to calculate the orientation polarizability alpha naught, similar equation is used, that is mu naught divided by E, or mu naught is equal to alpha naught into E. The uniqueness of this kind of dipolar polarization is that it is largely temperature dependent. Electronic and ionic polarizabilities are temperature independent, but they depend on molecular structure, but this orientation polarization depends largely on the temperature. The other type of polarization mechanism that happens in a dielectric material is space charge polarization. This kind of polarization is possible in multi-phase dielectric materials. In some dielectrics, few localized regions of different electrical resistivity exist, as shown here. Such materials are known as multi-phase dielectric materials. Charges usually accumulate within the regions of lower electrical resistivity. they arrange randomly in absence of electric field. When a field is applied, positive charges move towards the boundaries lying on negative potential region and vice versa. Such a polarization within the localized small regions is known as space charge polarization. This type of polarization is very rare in dielectrics because while preparing the dielectric materials for practical applications, utmost care is taken such that such localized regions of different resistivities do not arise. Therefore, usually for practically usable dielectric materials, the total polarizability is due to the electronic, ionic and orientational polarizabilities, because the space charge polarization is ineffective in the practically used dielectric materials. These are the four types of polarization mechanisms. Now let us look into the frequency dependence of polarization mechanisms or dielectric constant in alternating electric field. Because in the direct electric field, the dielectric constant is constant. But in an alternating electric field, dielectric constant varies with the frequency. You can see from this diagram that the polarizability or relative permittivity are varying with the frequencies. We have taken the frequency starting from 100 Hz to a very high frequency about 10 power 18 Hz. As I mentioned, dielectric constant, that is relative permittivity, is static in the static electric field, but it is inversely proportional to frequency. So when a dielectric material is subjected to an alternating electric field of certain frequency, for the smaller values of the frequency, dipoles can reverse their orientation every time when polarity of the field changes. As long as the frequency remains smaller, for example, when it is below 10 power 6 Hz, dipoles can follow alternations of the field, and the dielectric constant retains the value equal to that in the static field. Whereas when the frequency exceeds this range, the dipoles cannot follow the speed of alternations of the field. Hence, the dipolar polarization ceases in the frequency range above 10 to 6, 10 power 6 to 10 power 11 Hz in this range. In this range only ionic polarization and electronic polarizations can sustain. Orientational polarization is possible only in the lower frequency range. When the frequency exceeds 10 power 12 Hz, even the ionic polarization mechanism will stop, and only electronic polarization will continue in the higher frequency range. Let us say about 10 power 12 Hz and up to 10 power 16 or 17 Hz. So this kind of frequency dependence of polarization mechanism is because of the natural frequencies of the dipoles or ions or the electrons. You know that the dipoles are heavier in mass as compared to the masses of the ions or the electrons. Therefore, natural frequency is obviously smaller for the dipoles, and hence they can resonate with the applied field frequency in the lower frequency values, and for the intermediate frequency values the ions can have the ability to undergo polarization because of their natural frequency matching with the frequency of the field in this range. Whereas the electrons, being very small particles as compared to the ions and the Dipoles, they are of very lower masses, therefore they can have very high natural frequency, hence they can polarize even at very high frequencies. So what do we understand from this? At very low frequencies, all the three types of polarizations are possible: electronic, ionic and orientational polarizations. Whereas in the middle range between 10 power 6 and 10 power 12 Hertz, only ionic and electronic polarizations are possible, and beyond 10 power 12 Hertz in a given material, the electronic polarization can sustain. So this is how the relative permittivity or polarizability depend on frequency in an inverse manner.